Hello, this is Pat Hindle, Technical Editor at Microwave Journal. It is my pleasure to welcome you all to this session in our Technical Education webinar series on MMIC Amplifier design. Before we start, there are a few items that I'd like to bring to the attention of our viewers. Today's presentation is approximately 30 minutes long, after which time we'll hold a question and answer session with our presenter. You may submit a question through the website at any time during the presentation through the Q&A box. The questions will be held until the end of the presentation, and then we'll answer them. Please address your questions to all presenters, which is the default setting in the Q&A box. This presentation will be archived and available for viewing later on in the events section of the Microwave Journal website. Also, if you'd like more detail in the slides, simply click on the lower left-hand side enlarge button. Today's webinar is sponsored by Mini-Circuits, a global leader in the design, development, manufacturing, and supply of RF and microwave components to a wide range of markets, including telecommunications, broadband wireless, instrumentation, defense, and aerospace. This webinar offers an insight into MMIC amplifier design approaches from semiconductor technology selection, circuit architectures, characterization, and testing to final market released MMIC amplifiers. Along the way, some key differences in the approach between mini-circuits and typical market products will be highlighted. Our presenter today is Ted Heil, Vice President and Chief Operating Officer at Mini-Circuits. With over 25 years of electronics industry experience, prior to joining Mini-Circuits, Ted was at Volex, a manufacturer of cable assemblies and power cords, where he held the position of President of Volex's Interconnect Division. Prior to that, Ted held senior management positions at PowerWave Technologies and Vice President of Product Development and Vice President of OEM Sales there. Ted joined PowerWave after years in a variety of engineering, sales, and general management positions in RF and microwave space industry, including American Technical Ceramics, MITEC, and MACOM. Ted is a radio frequency engineer with a BSEE degree from Villanova University and has taken graduate courses at New York Polytechnic University. And also with us today, just for the Q&A session, will be QY Lee. QY is a senior design engineer at Mini-Circuits and is responsible for the design of a wide range of MMIC and passive integrated semiconductor products, including RF, microwave, and millimeter wave MMIC amplifiers, couplers, splitters, and hybrids. With more than 20 years of industry experience, QY has an in-depth knowledge and practice in gallium arsenide and passive silicon devices. Prior to joining Mini-Circuits, QY held a variety of technical positions at HP, Agilent Semiconductor Development Group, including designer and R&D project manager. So at this point, I will hand off the presentation to Ted.
Okay. Thank you, Pat. I hope everyone can hear me. Thanks very much for attending the webinar today. During our discussion, we're going to cover a wide range of topics all along the line of the MMIC amplifier design experience. We're going to touch on the variety of different technologies that are available to us and to others who are designing semiconductor amplifiers, RF semiconductor amplifiers. We're going to talk about the choices that we make in the selection of those processes and materials and topologies, and then we're going to address the multidisciplinary approach to MMIC amplifier design. First, let's talk about the types of materials and technologies which are available to us in selecting, in beginning any kind of design process. There are a wide range of materials that are available in the market today, ranging from silicon to gas to gallium nitride. Just touching on each of them individually, let's first talk about silicon. Silicon is by far probably the most common choice for an RF semiconductor material. It's been around for a very, very long time. It has broad range of applicability. You can embed CMOS or bi-CMOS structures, and you can integrate not only RF elements within the semiconductor, but you can also integrate those RF functions with control and logic and processing capability. So this technology, silicon, is a wide-ranging solution for a lot of applications. There are some limitations with silicon technology in terms of frequency and power and noise, but a lot of these limitations are being overcome, particularly in the last several years. Fabs like TSMC and IBM have made significant progress, particularly in some of the low nanometer solutions, in offering higher and higher frequency options. And with this type of solution, you can add all of the circuits to make a complete radio on chip. And what we're seeing now from the likes of Qualcomm and Broadcom is a range of single function or single chip solutions that can cover everything from the transmit, the receive, the low noise amplifier, the linearization, baseband processing, and all of the controls to make a complete handset or virtually a complete base station, whether it's a femtocell or a picocell. So silicon has its roots deep in our industry, but it's also an ongoing force for RF and microwave solutions. The other thing about silicon is you can get extremely large format. 12-inch wafers are common both at IBM and TSMC. So in a 12-inch wafer, you think about the scale, the number of chips I can get per wafer, and that really drives the cost. So silicon, from a cost solution on a per unit basis, is extremely attractive. That's why you see it in use in mobile devices, set-top boxes, handsets, and really dominating the industry. And when you combine some of the improved performance with the low nanometer counts semiconductors, it's really threatening some what was traditional RF technologies like GaAs for low noise and for front end options. You know, the same benefits of scale and size and cost also create somewhat of a barrier to enter in the silicon, using silicon. Your tool sets are very expensive. Your access to fabs is somewhat limited, so you need to be a large player, a large consumer of devices in order to be able to get access to these fabs. And your minimum and your foundry costs are extremely high compared to some of the other options that are in GaAs or SiGe. The other thing is your minimum order sizes are very, very large. So it's really fit for a high volume application. It's really fit for a committed design. It's great for integration. It's great for full function solutions, systems on chips, but it does have its limitation. The next semiconductor solution we'll talk about is silicon germanium. This has been around for also a fair number of years and is a really nice compromise between the benefits of silicon and some of the higher performance devices for higher frequencies such as gallium arsenide. Silicon germanium, there's a number of fabs that are out there today using this. Most of these are captive fabs. That means that they do not accept use by anyone on their process. But it has some, the solution, the substrate has some very nice features. Okay, so it works well at high frequencies. The noise figures are pretty good that you can achieve from silicon germanium. But one of the real big features and the real benefits is that you can make extremely low current consumption devices. So maybe this is not important for every application, but if you're operating on batteries or your remote applications like automated meter reading where you're dormant for days and weeks at a time, and then you have to transmit and a battery has to last years, silicon germanium has really found a home and is a great alternative to pure silicon or some of the higher current consumption technologies like gallium arsenide. On the power side, let's talk about both silicon carbide and gallium nitride. Both of these, for the last 10 years, I would say, have been vying for a lead position to compete with silicon, whether it's LDMOS or gallium arsenide for the power market. In the last 5 years, I would say gallium nitride has really taken the lead and surpassed anything that silicon carbide can do. It started with companies like, at the time, it was Udina, which became Sumitomo, and now is heavily dominated by companies like Cree. TriQuint it has gallium nitride fab capability, and there are a number of other merchant fabs out there who are pursuing a gallium nitride option. So gallium nitride has come into its own only in the last 2 or 3 years. Because of the cost associated with it, it really had a difficult time achieving any kind of adoption outside the military markets. I think now we're on 4-inch wafers at Cree, so that the cost effectiveness of gallium nitride has improved significantly. But really, the big thing that I see in pushing the adoption of gallium nitride is the efficiencies that you can achieve out of this. In a power amplifier, whether you're using it in a balanced or a Doherty configuration, you can achieve significantly higher levels of power added efficiency from gallium nitride over what you can achieve out of silicon LDMOS. And the total cost of ownership equation of any kind of a system, whether it be, and it includes not only the purchase price, but the ongoing operation expenses, come into play in the selection of the device. So because the efficiency is so much better with gallium nitride and energy costs are so high, with the proliferation of picocells and femtocells and all of the multiplied energy effect that you're going to have, we see that the market is becoming much more acceptable to paying a little bit more upfront for a gallium nitride device and reaping the benefits on energy consumption costs in the long run. So our opinion is that, or our position is that we see gallium nitride is really going to take the lead, is taking the lead, and will take the lead in the future on the power front. There are some more esoteric materials such as indium phosphide and more exotic materials. They're used in more special applications like higher frequencies, the mid to high millimeter wave bands. Indium phosphide has cutoff frequencies well in excess of 100 gigahertz. So it was relegated for many, many, many years to the R&D labs. For those of you who remember, Hughes Research Labs, or TRW, we're developing in-gap devices for millimeter wave radar, and then ultimately for the military applications, and then ultimately for collision avoidance. But now these devices are also finding commercialized home, not just in automotive, but in the E-band backhaul for point-to-point radios for the new femtocell that are used in the LTE rollout. So although it's not really prolific, we do expect to see more and more applications making use of indium phosphide in the next 5 to 10 years. So I jumped over gas because I really want to spend time on gas in respect to why mini circuits is selecting gallium arsenide as its primary vehicle. Well, first of all, we see gallium arsenide remains probably the best compromise solution for the RF microwave bands. And we're talking about bands that start in the 400 or 500 megahertz, but really extend up in frequency beyond 6 gigahertz. Silicon's got its place in the lower end of that, but can't translate, or today is having a difficult time translating higher and higher frequencies. Silicon germanium does, but it doesn't offer the versatility of gallium arsenide. And for companies like Mini Circuits, we select and for any company, we select our materials and our topologies and our approaches based upon what drives our business. So we are not focused on extremely high volume handset or subscriber level products. We are focused on the mid-level, infrastructure level markets where the volumes are not 1 million pieces a day. They're significantly smaller. They're still large enough that we need to have a highly efficient, cost-effective product, but we need to have the versatility to be able to support a wide range of applications, and we need to be able to optimize performance for those fringe or niche applications. And GaAs offers that, because gallium arsenide, we can use it up to 40, 50 gigahertz, so it has a wide frequency coverage. We use it down to 100 megahertz or even down to 10 megahertz and less. So that's the frequency coverage. It also offers today what we believe as the lowest noise figure option in the industry. So in the last five years, Mini Circuits has really made a big push on low noise devices, and GaAs offers us the best option that we can use to drive low noise figures. We're capable now of F-mins in the neighborhood of 0.18 dB, okay, measured noise performance. We also can use it for its high linearity. We can get third-order intercept points for 150 milliamps of current. We can drive IP3s into plus 42, plus 43 dBm. So it's an ideal material for us to leverage a large variety of different designs to cover a lot of different applications, and that's why we select GaAs. You know, one of the other things about gallium arsenide is there's a large number of merchant fabs out there, whether it's Win Semiconductor or TriQuint. Those are companies who offer fab services to anyone, and the cost of it to enter this market is not as steep as it is with the silicon services. So you can make use of very common design tools like AWR and ADS, and work with a merchant fab and generate, for a reasonable cost to enter, a good solution. At Mini Circuits, using gallium arsenide, we focus on two basic approaches to our amplifier designs. And simply they're using, one is a p-hemp approach, and the other is an HBT approach. On p-hemp, both designs are using gallium arsenide as the substrate. On the HBT designs, we use an in-gap layer for the epi, the emitter structure, and p-hemp, it's a full gas structure, hemp structure. And we use these for two. Each one of them has its own benefits, its advantages, and somewhat its disadvantages. The p-hemp approach, the p-hemp design structure, can give us clearly the best noise figure that's out there in the industry. This is where we're currently achieving 0.18 dB F-mins. We are migrating the majority of our designs from depletion mode over to enhanced mode, and this gives us the ability to offer single voltage solutions to our customers. So you no longer need a negative bias on the gate. It makes it very easy to use and easy to implement in circuits. It also has, E-mode p-hemp also has a significant amount of gain. In the 1 gigahertz range, we can get gains in excess of 20 dB for a single stage. So it's very efficient if you're looking for high gains. One of the things, the drawbacks is that you have to control that gain. So an EP-hemp structure, if we use it in a single-ended or in a cascode design, you really have a very large 1 over F slope. And to control that, you need to put feedback in. And feedback is not so simple here because it has some negative effects on noise figure and IP3 and P1 dB. On the other hand, the in-gap HBT is an approach that we have been using for a very long period of time, whether it's in a Darlington configuration or a cascode, to create extremely wideband, very high utility, medium power amplifiers, up to 1/2 watt, 1 watt solutions, up to around the 4 to 6 gigahertz range. It's an extremely robust technology. We can get ESD levels, intrinsic ESD levels over 1,000 volts. So you have a very robust, high reliability product that's used extensively throughout the RF and microwave industry, and that's why we make use of it. Now, using both of those technologies, we deploy a number of different circuit architectures on those substrate materials. One of the most common ones that we use is referred to as the Darlington configuration. This configuration has been around since the 50s. It's been used in discrete amplifiers for a very, very long time. It's also been used in MMIC amplifier designs since the early to mid-'80s. As I recall, I mean, in the Avantec days, which were some of the earliest MMIC RF amplifiers that were put on the market, the dominant structure was Darlington, and it still has some very, very good advantages that we make of use today. First of all, it can be implemented in either a bipolar, as shown in this diagram, or it can be implemented with FETs. It has some intrinsic stability features that enable it to be somewhat immune to swings in current and voltage. It also is extremely good for a good structure for integrating with on-chip matching solutions so that we can get very nice controlled flat gain over very, very broad frequency ranges. In the configuration, the second transistor, Q2, that you see on the screen, it's slightly larger, and that's where all the power comes from. And even though it is used in our designs for a lot of our medium power solutions. It is not the best low noise figure approach out there. Usually there's, in fact, we don't show it here. There are bias resistors that go into the base or the gate circuit, and those bias effect resistors, they give some benefits of creating a feedback path to flatten the gain, but they also have negative effects on noise figure. So this is not an approach that we're using for our ultra low noise designs. The cascode approach, on the other hand, is the approach that's giving us the lowest noise designs. This is one that's giving us the 0.18 dBs. This is the design that has a very, very high intrinsic gain built into it, and because of the nature between Q1 and Q2, there's actually a very low impedance between the two transistors. You reduce the capacitance, the intrinsic Miller capacitance in the structure, and you can get very, very high frequency designs. We make a lot of use of this. If you look at our PMA series, makes extensive use of this circuit, and we're able to make high gain, low noise amplifiers over very, very broad frequency ranges. The final architecture that we'll talk about today is a distributed amplifier, and this has been around also for a very, very long time. It's a traveling wave structure, and you can make extremely broadband amplifiers at high frequencies. Both the Darlington and the Cascode, or single-ended lossless feedback, you can make multi-octave designs starting from very, very low frequencies, but you have limitations. The feedback falls off and loses its effect as you get up to, say, around 6, 8, 10 gigahertz. Our Darlington configurations, we push them up to around 10, the same thing with the Cascodes, but above that, they fall off. So in those cases, we replace our designs, the circuit topology, with the distributed approach. And we can make extremely broadband designs, 1 to 20 gigahertz, 0.1 to 20 gigahertz. 6 to 40 gigahertz can be made using this approach. And the more number of devices you can stack, the wider the band. The downside of this is chip size. Because you're trying to put a large number of devices in the gate line and the drain line, you start to use up a lot of chip real estate. And chip real estate results in cost, okay, and packaging difficulty. Also, the design is traditionally not used in low noise, and in fact, we don't use it in any low noise devices. But it is very effective in making broadband, multi-octave, medium power solutions. 100 milliwatts, 200 milliwatts, a half a watt, and even 1 watt, 18 gigahertz structures are out there today using a distributed or traveling wave architecture. In addition to the basic topologies, a good amplifier design takes into account a number of other elements to make the design useful, to make the design reliable, rugged, and repeatable. One of the things that Mini Circuits adds to almost all of our designs today is an active bias architecture. This is not unique to mini circuits. There are a number of MMIC amplifier providers in the market today who are using this. We give a good example of the circuit in our SAV series data sheet. It's typically referred to as a current mirror. It's basically a negative feedback structure that we embed right on the chip so that we can ensure that the bias on all of the transistors is constant over changes in voltage, VCC, constant over changes in temperature. And it's a good tool and a good practice to add this on any of your MMIC amplifier designs. And for those designing with discrete transistors, you're probably making use of the same circuit in a discrete implementation around your transistors. And as I mentioned, the details on the circuits are available on our website. Another feature that we add, particularly on the PHEMT designs, is we add ESD protection on chip. So let's talk a little bit about ESD. ESD damage is the fear of almost every circuit designer and every manufacturer. It's a device that is damaged due to ESD may not show up as an immediate failure in test. It may not even show up in the first week. It may not even show up in the first month. It could present what everyone fears in terms of a latent defect that may manifest itself years down, and you don't know about it as the designer or the manufacturer. So, because you can't test for it. So what we do, and what a lot of people are doing, is to take all the precautions and steps to assure that our parts can meet high levels of ESD spikes before we put them into the market. Every part that we design and manufacture is characterized and rated for its ESD susceptibility. You'll see ratings like human body model, HBM, or machine model, MM, and that's how the industry rates the ESD performance of any particular device. Mini circuits, our rule is we do not put a class 0 part on the market because of all of the reasons we just discussed. Everything that we put on the market must be at least a class 1A, which is 250 volts, human body model, and almost all of our parts are higher than that. The most critical part, or the most sensitive parts that we make, and everyone in the market is making in gallium arsenide today, are the PHEMT structures. The gate structure is more fragile than, let's say, the junctions on a bipolar design or an HBT approach. And in order to get those gate structures as robust as possible, what we will do is we will embed on all of the ports, whether they're active ports, RF ports, or even passive ports on the device, which can be exposed to the customer, we will add protection diodes. Basically, it's a simple PN junction that we embed in the epi layer of the device. We employ them in antiparallel pairs so they shunt and reflect very, very high voltage spikes that cross the thresholds. And we are able to, with almost any PHEMT structure out there, we can now push levels well above the class 1A. We also get a little added benefit because of, when we believe it's because of these PN junctions, particularly on the input, on the RF input. They have a very high survivability for input powers. What used to be a common limit of maybe plus 15 dBm for maximum input power survivability, we're now able to push that over 100 milliwatts, even 200 milliwatts. And we think a lot of the benefits that we're getting out of the ESD diodes is enabling those higher power RF survivability. Another thing that we've developed, in fact, we have a patent on it, is we add a transient protection on the output of the devices. Not only are we worried about voltage spikes from ESD, but in any circuit, there are things that are unplanned that happen that may drive large voltage spikes down the RF path. These would not classify as ESD, they would classify as general transients. And we've developed a structure to put along either the collector to emitter or drain to source, where we actually we have a threshold device that trips and sinks all of that excess voltage and current down to ground. And adding circuits like this on your amplifier structures, on your MMIC designs, on chip, are things that you can do, that we do, in order to help improve the long-term reliability and the performance of the device. Another thing that we and almost every designer out there is worried about and concerns themselves about is junction temperatures, operating within the safe operating temperature of the device. All of our devices are characterized, as everyone, for what is the actual operating junction temperature at the operating base plate temperature. Typically, we try to stay below 150 degrees C. That's where the semiconductor limits are, and we qualify every part that we put into the market that we can achieve those levels. But then what we also do on a wafer lot by wafer lot is we monitor the performance and the repeatability of that junction temperature. What Mini Circuits does is we employ and we embed a diode, a thermal diode, that we monitor the IV characteristics of it near the junction. There's one die per reticle that we sample on a wafer lot basis, and this is the way that we can confirm repeatability lot to lot. And it's that repeatability that gives us the confidence that we can put a highly reliable product in the market. There are other ways to do that. You can do thermal images and scans on each wafer lot as part of the qualification, and I'm not sure what others do, but these are the techniques and tools that all circuit designers are using so that they can assure a high reliable product going into the market. So those are some of the topologies and the materials that we and others utilize in designing products. But there's a lot of other elements to the design process, and designing a MMIC amplifier is really more of a team sport than an individual contributor. It's not an engineer sitting in his office with Cadence or ADS and the design kit from the fab and the design rule checker and developing a device. It really requires a team to bring that product to market, and there's a lot more than just circuit design involved. The circuit design is only a single element. After the part is designed and after all of that work is brought to a tape out and you get your first parts, there is a significant amount of effort in qualification and characterization. And characterization is a multi-week event. It takes a large team to prepare a whole battery of tests to fully characterize the part, to see A, do we achieve our design goals, and B, to understand the limits of the part, so that when you create your data sheets and your design and your documentation for your customers, you can put the part into the market with a high degree of confidence. We use the latest equipment, for whether it's from Agilent or Rode or Anritsu, to analyze and to measure our parts. We do load pulls on all of our parts to see what is the effective impedance, to check stabilities, and to provide optimal data and optimal performance characteristics to our customers on the packaged part. We put every part through a battery of qualification. The JEDEC standard, JESD 47, does a fantastic job in outlining for everyone. It is the playbook by which you qualify your parts. And Mini Circuits and all other semiconductor manufacturers and designers are using it as the Bible. We put our parts through high temperature operating life, which is specified in JEDEC as 1,000 hours, 80 units at 1,000 hours, greater than 125 degrees C junction temperature, and less than TJ max. At Mini Circuits, we pushed that to 5,000 hours because of we're a little bit conservative, but we really want to assure our customers of the highest quality and the highest reliability. The other areas of multidisciplinary design are in the packaging. This is typically not done by your circuit designer, but you'll have a package design team. And these engineers are making use of a wide variety of materials, whether they're plastics or ceramics or epoxies, designing the lead frames, and they're really focused on a few things. They're focused on protecting the device and getting the heat out and getting the lowest parasitic package to have the least degradation on the performance of the chip. And this team is using all the tools that are out there, whether they're the same level of sophistication and simulation that go into the circuit design, go into the package design. Finite element analysis, thermal analysis, to create the optimal package solution for the part. One of the other things that package engineers are looking at, we talked about thermal, but also protection. Since the vast majority of packaging today is plastic, and that's where we package most of our parts, we have to be extremely careful and cautious on how we embed the semiconductor in the plastic. One of the biggest concerns is delamination of the plastic, and that could happen if there's not a good adhesion to the lead frame and adhesion to the device. And the way you verify that is through MSL testing. MSL testing is done through a scanning acoustic microscope, and you're looking for voids or potential voids in the device. They show up, and they're very obvious when you see them on the red. They show up as a red screen, and what they do is they give you indications of potential sources of delamination. Every good packaging company out there is performing MSL testing on a regular basis on each of the packages through a normal cycle of test. And if you're not doing that, and if they're not doing it, they are adding an unwanted element of risk. So moisture sensitivity is something that we put a lot of focus on. Now, one of the things I will mention with regard to semiconductor packaging, very few companies today, very few semiconductor manufacturers are actually packaging their own devices. There's quite a few packaging companies out there throughout the world, whether it's in the U.S. or in Asia, who are taking on the vast majority of plastic packages. At Mini Circuits, we package our own devices, and we have about 200,000 square foot in Malaysia that's devoted almost exclusively to plastic packaging of our semiconductors. And we do that because our volume really is in the mid-level volumes, and setup times and setup repeatability are critical. So we can have dedicated setups given to specific packages. We don't have to worry about retooling and tool-up times, and we can create an extremely reliable workflow that we've enjoyed a lot of success over the last several years. MSL testing is part of our daily life. In our Penang facility, we are running MSL tests on production lots every day, 6 days a week, and that's all part of baking in or building in the reliability into the design and to the development process and to the manufacturing process. So those are the things that we focus on in designing a product. And now I just wanted to spend the last few minutes of the presentation just going over a couple of the real-life examples of what we just talked about, and I'll just touch very briefly on them. This is our Lee series amplifiers, and we talked earlier about the Darlington configuration, how that configuration is extremely adaptive for wideband, flat frequency performance devices. This is a modified QFN package that we make. It's a plastic encapsulated solution with a very low inductive lead frame. So the lead frame is contributing or is adding very few parasitics to the chip. And take a look at that performance. We're up to 8 gigahertz on it. This is a gallium arsenide HBT design that is going from near DC to 8 gigahertz. Obviously, many, many, many octaves. And that's making use of that Darlington configuration. We use that same configuration and optimize for power. So now our Q2 is significant size on Q2, and we're able to push the output powers over optimized frequency range up to close to 1 watt, and we'll be releasing 1 watt designs over the next several months. with outstanding efficiencies. Even for gallium arsenide, we're getting better than 50% PAE. We also use we mentioned PHEMT. One of the real struggles with PHEMT is getting flat gain performance. We are able to add feedback to some of these circuits. We take a little impact on noise figures. So you see here we're offering noise figures around 3 gigahertz. But here's a PHEMT design that goes from 5 to 2150 megahertz. One part that is very, very high dynamic range, plus 37 dB MMIC3. This particular design is centered for 75 ohms and is used in the cable TV markets. And then we talked about noise figures. Here's a quarter micron PHEMT. So this is that PHEMT structure again. If I showed you the gain coverage, you would see a very sharp slope. So that means there's a very sharp drop in gain versus frequency. But it does operate up to 3 gigahertz. And this has best-in-class noise figure, 0.18 dB noise F-min at the optimal impedance. So we're able to deliver less than a quarter of a dB noise figure to the customer in 50 ohms at less than a gigahertz. So those are, just summarizing. So we give you some examples of the techniques and the topologies and the materials that we talked about, and we drove it all the way through to real life, very measured performance by the use of these techniques. So with that, I'd like to turn it back over to Patrick, and any questions you may have.
Great. Thank you very much, Ted. Excellent presentation. It really shows you all the different considerations that need to be accounted for in a MMIC design. It really takes a lot of different groups and a lot of different expertise to design a good product. So we'll get right to the Q&A session. We have a lot of questions actually coming in, so let's get started. In comparison to SiGe technology, how expensive is gallium arsenide compared to SiGe?
Well, SiGe can be made in larger format wafers. The gallium arsenide on a per wafer basis or on a per millimeter wave basis is going to be slightly higher. Let's say it may be as much as 2 times the price of silicon germanium. So if you have access to a fab and you can design on silicon germanium, can be very, very cost effective. It's not as cost effective as silicon, but it is probably half the price of gallium arsenide wafers.
Okay, next question is about a question on measurement. Do you measure on wafer or on board or both?
It depends on where we are in the process. The very early measurements are done, and we're talking about RF measurements. The very early measurements we do are on die. So we're not making the RF measurements on wafer, but we are extracting the die, and we are doing a lot of our characterization, or our load pulls, and our designs with on-chip measurements. As we move to the final qualification and characterization, of course, those are all done at the package level.
Okay. Does Mini Circuits guarantee an IP3 as a spec?
Depends upon the part. For example, we have some very high IP3 parts that we do guarantee in our catalog data sheet what the IP3 is. But one of the things that we can do, and really this is consistent with the type of business that Mini Circuits does, is we will work with any customer and come up with a custom solution, a custom specification solution. That doesn't mean that we're making a new design or a unique design for that customer, but if a customer wants us to guarantee IP3, we will work with them, and then we will screen for that IP3 level.
Okay, next question. If someone is interested in a low-noise MMIC that operates from 1.4 to 5.5 gigahertz with a reasonable VISWAR and flat gain, any designs coming out soon that would meet this, and looking for a low noise figure of about 1 dB?
1 dB up to 5 gig a broadband, that's a real challenge. We don't have anything in the pipeline specifically that type of noise figure over that wide band. We do have some designs that are more in the range of 2 dB that are coming out. They're starting a little bit higher frequency and they end in higher frequency, but you know, the 1 to 5 gig range, it should be achievable to do about 2 dB noise figure. Like I say, I don't have anything in the design pipe right now, but it's possible.
Okay. There are many new devices coming out that can handle RF inputs, CW power levels greater than 200 milliwatts. What's the driving factor for this improvement?
Well, I'll tell you from our perspective, if we're looking at the applications that drive this requirement are unwanted signals in the receive path. It's a very dense EMI environment out there, and what all systems designers want to do is optimize their performance. So if they don't have to put any kind of external limiter protection up front and sacrifice the impact on noise figure and transfer that power directly to the device, they're going to do that. And that's why we're seeing the need for power levels in the 2 to 400 milliwatts survivable range. What's enabled that is, A, some improvements in the semiconductor, okay, in the either the 0.5 or the 0.25 micron wafer processes, but also, as I mentioned a little earlier, we're embedding these ESD diodes that are giving us additional benefits in the ability to withstand and survive in these very high levels.
Okay, sticking on that same subject, kind of what ESD performance do you achieve through your ESD protection diodes?
We can take what was traditionally a class 0 process and drive it to class 1A. That means 250 volts. We can take a 250 volt process and drive it to class 1B, which is 500 volts.
Okay, next question. What tools do you use for EM simulation?
For EM simulation, and I think we're referring to mainly on the packaging, we use a finite element analysis. Our dominant approach is HFSS, which will not make Agilent happy.
Okay, another question was, what are some of the general markets that Mini Circuits is in?
So Mini Circuits is a bit of a Walmart. We service over 20,000 customers in a wide range of markets, and that's really been the history of the company for the 45 years we've been in business. We're not so driven by any one market, but in a generalistic footprint, we cover everything from telecommunications, and in the telecommunications space, it's the infrastructure side. We do nothing on the subscriber and mobile applications. So we're in base stations, we're in point-to-point, we're in backhaul, we're in, those are the predominant telecommunications applications. Defense and aerospace still is a significant portion of our business, whether it's surveillance, radar, receivers, communications, air-to-air, air-to-ground, ship-to-shore, everything. VHF, UHF. Also, satellite communications is a strong market for Mini Circuits, whether it's the VSAT side all the way through to the large Earth stations. For us, we've seen a wonderful adoption of RF technology in the broadband optical solutions, and that's that really drove a lot of our 75 ohm development, whether it's cable TV, passive optical networks, MoCA, RFOG, and then we do a lot in test and instrumentation, and that covers maybe 50% of our business. And then there's a very long tail of a wide variety of markets and applications that make up the vast majority of our customers.
Okay, and related topic, does Mini Circuits provide foundry service?
We are fabless. We do not provide foundry service. So that means we do not own a fab. We use a variety of different fabs that are out there, whether they're in Asia or North America. There are two models in the semiconductor space. There is captive and merchant, and there are many companies like Skyworks and TriQuint who own their own fabs, and almost everything that they develop is done on their fabs. They may outsource a little bit of it, but these are the captive companies. Then there are companies like Mini Circuits, which we chose, and it's a strategic choice of ours, to not invest in a foundry, not invest in a wafer fab. And in our cases, we create strategic alliances with the fab partners that we want to have. And that, by the way, I will make a point, that is real important, because having a good, strong relationship with your fab is critical. They provide you a service that you can't live without. And the stronger the relationship that you have with them, the better you understand their processes, the better communication you have with them. You can get, you really need to be involved with them very early up front in the development process. You also need to use them to help generate your roadmaps of where you're going, in the 5 to 10 year frame.
Okay, and does Mini Circuits have an interest in gallium nitride?
Well, of course we have an interest in gallium nitride, and we are participating in GaN in the R&D phase only. Right now we do not have a product rollout strategy for GaN.
Okay, what's the maximum frequency amplification that you plan to ship in the next couple of years?
40 gigahertz. We don't have a roadmap that gets us to E-band.
Does the ESD diode affect the RF performance and noise performance of the circuit?
Yes, because we're putting these PN junctions at all of the DC and the RF ports. Obviously, we have we touch the input of the input gate of a low noise MMIC. And as a result, we're seeing an impact of around a tenth to even up to 0.2 of a dB impact on noise figure.
Okay, and I think you may have showed this, but can a feedback external to the MMIC be used to flatten the gain for devices such as the GVA-63?
I wouldn't use it on the GVA-63 because it's pretty flattened to begin with, but you can use it on others, and we have developed some application circuits for employing external feedback, whether it's true output to input or shunt feedback to flatten the gain. It's more appropriate on some of the low noise amplifiers like our PSA-4 5043, which has a really, really sharp 1/F performance.
Okay, when would you select PHEMT versus in-gap HBT for a specific design?
It's all about the application. The in-gap HBT is really more suited for broadband, medium power solutions. The best noise figures we can get out of an in-gap HBT design are about 3.5 dB. So I wouldn't use it for a low noise application. In the case of low noise, I would go exclusively with a PHEMT approach where we can get that extremely low noise.
Okay, what's the maximum allowable junction temperature for these MMIC amplifiers? Can any technologies operate at higher levels?
For gallium arsenide, we have an internal design rule of 155 degrees C. Our fabs tell us we can push that to 160, and they've given us all of the supporting documentation, but being a little conservative, we derate a little bit. There are higher junction temperature capabilities out there. Gallium nitride can push that higher, and those are really aligned for and designed for the power applications.
Okay, 1/F noise is becoming a problem in high-end instrumentation. HBT seems the way to go. What's the highest frequency HBT device you're offering? Well,
I think the 1/F noise is more a function of the coarse material, the base material. And even though we build HBTs in gallium arsenide, you will not get the corner noise, the 1/F noise that you would get out of silicon germanium. Now, for us, the gas HBT designs, we push them up to about 10 gigahertz, and they start near DC. But to be perfectly honest with you, I know we don't have a silicon germanium offering, but you will get a significantly better 1/F noise out of a silicon-based solution.
Okay, does Mini Circuits sell bare die of any kind, and is there a minimum buy?
We are piloting the release of our current MMIC amplifier family as bare die. We're working through the final processes now and the handling and the support, and we've got a few customers that we're sampling and sending to. With regard to the sales strategy, what we'll do is we'll offer down to 10-piece minimums, because we know a lot of customers out there, and that's really, we're trying to make it easy for the customer. So we're not going to give you an MOQ of 100 pieces or whatever. You want to buy 10, we'll sell you 10, and we're going to have them in traditional Mini Circuits fashion. They will be stocked in sealed bags so that we can ship same day 10-piece quantities.
Wow, that's excellent. What's the final package part testing performed on, like an LNA or PA? What are some of the typical measurements?
What we do is we'll do at the packaged, we will do gain, current, compression, possibly IP3 if it's an high dynamic range part. We're generally not performing 100% noise figure measurement. What we're doing is we're doing noise figure on a lot qualification basis.
Okay, does Mini Circuits have any low phase noise amplifiers?
I would put those in the same class as 1 over F. So additive phase noise, for whether it's a coherent radar or something like that. It's first of all, it's a difficult to measure part, but difficult to measure parameter. But you can, your limits and your performance is going to be based upon the fundamental semiconductor. So if you need a low additive phase noise part, you would probably want to look to silicon to get the best performance. What we can do is, if we get the interest, is it's a fascinating subject to do an additive phase noise measurement. We can do some additive phase noise measurements on the HBTs to see how good they are.
Okay, do you offer custom super components? What's typical NRE?
Yes, and maybe I should have talked about that. One of the things that we do, because, and it's enabled because we do our own packaging in our Malaysia facility, we can take multiple die and put them in a plastic encapsulated package, and we call it our MSIP, or Mini Circuit Systems and Package. And those are taking, either any of our own chips or chips that we can get available on the market today and integrating them to make a custom solution. Unlike a high-volume system-on-chip, this is a great mid-tier solution. So it's great for the quantities of thousands and tens of thousands. You don't need hundreds of thousands and millions of pieces to make that work. And for us, the NREs, I think, are reasonable in that they're in the thousands of dollars. They're not in the hundreds of thousands of dollars that it would cost you to do an SoC.
Great. Well, I think we've come close to our end of time here. So, Ted, thank you very much. It was an excellent presentation, and we had a lot of great questions and answers here in our session. So we appreciate it, and we thank Mini Circuits for sponsoring this. And everybody have a good day.
Okay. Thank you.